In this video, we will delve into artificial neural networks. To do this, let's recall that the idea of artificial neural networks is based on biological neurons. In biological neurons, we have an input at the dendrites, a type of processing at the axon hillock, and an output at the synapses. Artificial neurons also have an input, processing of the input, and an output. Such an artificial neuron is also referred to as a perceptron. What we haven't discussed yet is that weights are applied along the inputs, multiplying the input by a value w. Each input has its own weight by which it is multiplied. The calculation that happens within this illustrated neuron is simply the sum of the multiplications of the inputs by their weights. In our case, it's x0 times w0 plus x1 times w1 plus x2 times w2. This result then represents the output of this perceptron. Let's reduce the number of inputs. Then we can easily see that the previous calculation is a simple linear regression. From school, you might remember it as a graph with the function y is equal to m times x. Here, m is the slope and x is the value to be inserted. In our previous perceptron, the same function is described. Our weight w describes the slope of the function. Let's model such a simple linear regression in Python. So let's look into linear regression by converting kilometers into miles. And we will do this with the sklearn package that we have in our environment. So first we need to import sklearn, and we do it with writing from sklearn.linear model import linear regression. Furthermore, we will need numpy and import numpy as np. Now we execute this cell, and if we have installed everything correctly, it will turn out okay, and the packages are imported. For the next step, we need some training data, and I've prepared a little bit of training data so we can save some time. And the training data looks like this. X holds some distances in kilometers, and y holds the corresponding distances in miles. So 10 kilometers are roughly 6.2 miles, 15 kilometers are roughly 9.3 miles, and so on. I did some rounding here, so we might miss some decimals, but this will be all right for this use case. So let us execute this cell as well, and now we can start to build up the model that we want to use. For this, I will use a variable model, which will hold our model, and then use the linear regression which we imported above here, and we will feed one parameter into it, and this is the fit intercept, which we will turn on false. We turn this on false because we said that currently we do not have a y-intercept for linear regression and the neurons that we know so far, so we'll turn it off here as well. The next step, we want to train this linear regression model. And we do this by calling model.fit. And then we have to put in the x and the y data. If I execute this cell now, I will run into an error. And the error tells us what went wrong. It expected a 2D array, but it got a 1D array instead. So let's take a look. Yeah, this is true. I put in a 1D array, x had the shape 3 and no additional dimension. And this is something that the linear regression that we called here does not want. So we need to add an additional dimension. And I will do this with a reshape command. However, there are several other commands that do the same job, but it does not really matter which one you use. So I will just say x is now calling the variable x and reshape this array to -1, which is the wildcard again, and 1, which is the additional dimension we want to add. And yeah, we can do the same for y, but actually it is not really necessary for training, but I will just do it as it does not matter anyway. And let's see how the shape is now. And yes, so now we have an additional dimension, which was missing before. As soon as we have executed this cell, the old variables will be overwritten. So if I trigger this cell for training now, it will work out actually. So this is a little summary or the settings that we have made, and the model has been trained already. So let's look into what the model has trained so far. And I will call the model, call its coefficient. And this will have the value 0.6215, which is actually the slope of the function of the linear regression that we have calculated. So with this value here, I can already do some translation from kilometers to mileage. And for example, I can say 15 times this value, and the corresponding miles will be 9.32 for 15 kilometers. However, this is not really convenient to do this calculation this way, so we can directly let the model do the job. And we do this by calling the model and say predict. And within this round brackets, we can put in any data. And just remember, due to this issue with the dimensions, we need 2 square brackets and put in a value for which we want the prediction. And yeah, also this one gives out 9.3 miles in this case, which is the corresponding distance for 15 kilometers. We are now able to set up a linear model that can, for example, convert kilometers to miles. However, this only works if the desired function also goes through the origin. But what if our y-intercept is not at 0? Suppose we want to convert degrees Celsius to degrees Fahrenheit. The formula for that is degrees Celsius times 1.8 plus 32. With what we have learned so far, we cannot fully represent the entire formula. What's missing is the y-intercept, which we want to call the bias. The bias is simply another input in our perceptron. However, unlike the other inputs, it has a fixed value of 1. This 1 is also multiplied by a weight, denoted here as b. Our formula is thus extended by 1 times b. Since 1 times b is still b, we can simplify this part of the formula directly. What remains is the sum of the multiplications of the previous inputs plus the bias b. Let's simplify this perceptron, leaving only one variable input and the bias. This should remind us of the linear function from school. However, this time it has a y-intercept, allowing the function to be shifted along the y-axis. To come back to the example of converting degrees Celsius to degrees Fahrenheit, we will now create a linear function with a y-intercept in Python. I will reuse the script that I have used earlier, so in case you are using a new script, just remember to get the 2 imports of the linear regression from sklearn and numpy. So all the packages are imported. Yes, and we need some training data again, this time some data from degrees Celsius and degrees Fahrenheit. X is coding for some samples of degrees Celsius, and Y is coding for the corresponding samples in degrees Fahrenheit. So again, this minus 40 goes along with this minus 40. This minus 10 degrees Celsius corresponds to the 14 degrees Fahrenheit, and so on. I have already reshaped this array, so this time we will not run into an error. And the next part is already to set up the model. I will just give it the name model2, as we have already used the variable model in the previous part. And I will call a linear regression, which again, this one comes from the import at the very top. This time it is actually not really necessary to give it any parameters, because this time we want to have a y-intercept. But anyway, I will just put it in here to make it clear that this time the intercept is set to true. The next step is already to fit the model and to give in the x and the y data. Training was pretty fast again. And this time we want to get the coefficient once again, but also the y-intercept this time. And as a coefficient, the regression model learned a value of 1.8, which is correct. And as a y-intercept, it learned 32. So the exact values that we have expected actually. And of course, we can also do predictions with this model. Just to remember to get those brackets right, I would just put in 16 degrees Celsius, and in Fahrenheit, those are 60.8. Let's now address a topic that allows us to move from a single perceptron to a neural network, which is activation functions. We encounter a fundamental problem with the perceptrons we got to know so far. There's no real benefit to chaining perceptrons together. From a mathematical perspective, it makes no difference whether we chain two neurons to multiply the input of 5, first by the first weight of 2, and then again by a second weight of 2 to get 20, or whether we multiply the input of 5 directly by a weight of 4 to reach 20. Besides this problem of chaining simple perceptrons, we also face the challenge of scaling the final output of a model to get a value between 0 and 1, for example to show the relative probability that a traffic camera sees a car or not. The sigmoid activation function does just that and scales every input value to a range between 0 and 1. For instance, an input value of -6 is set to about 0 by the sigmoid function. In addition to the sigmoid function, there are many other common activation functions. Here are just 4 that are frequently used in neural networks. The 10H function, for example, scales to a range between -1 and 1. The rectified linear unit, or ReLU in short, sets all negative input values to 0 and performs linear scaling of positive values. The leaky ReLU and the ELU are variations of the ReLU and perform somewhat more complex scaling of negative input values. Such activation functions can then be applied to the result of our previous calculation. First, we compute the sum of the products of the inputs and the weights, and then we apply the chosen activation function. If we choose a sigmoid, the result will now lie between 0 and 1. Let's investigate the interaction between the bias and the sigmoid. As we already know, the bias can change the y-intercept. Under a sigmoid, this means that the function seems to shift along the x-axis. Meanwhile, the input weight affects the slope of the sigmoid, just as we learned in school. By the way, there's an informative thread on Stack Overflow about this topic if you want to learn more about it. The link is displayed. By using activation functions, it now also makes sense to chain multiple neurons together, because activation functions break the linearity of the model. We can now imagine that each neuron in the model calculates a new feature based on its input features. Simplified, one might imagine that we have precipitation, temperature, and soil moisture as input data. Then one neuron could calculate something like an infiltration rate. Another could calculate evaporation, and the next could calculate an index we might not know yet. By the way, the section at which we enter our features into the model is also called the input layer. All layers with neurons that do not output the final value are called hidden layers. And the final neurons that give us the result are called the output layer. But why do we actually need multiple hidden layers? Well, the universal approximation theorem states a neural network can approximate any continuous function provided it has at least one hidden layer. This means that with enough hidden layers, we can solve almost any problem. But of course, this is only theoretically true, because there is much more to neural networks than just building them. Although we are now aware of the components of a neural network, we have no idea how to let the model learn. So far, we have input values that are multiplied by weights to produce a result. But what if the result is simply wrong? For the model to adapt, we need values that are changeable to adjust the formula and thus the result. The only values in our neural network that can be adjusted are the weights attached to the inputs of each neuron. So we want to focus on how to adjust these weights. Imagine you are sitting in your apartment and you feel too cold. You go to the thermostat and turn it up a bit. Then you wait to see if you feel comfortable with the new temperature. If not, you adjust the thermostat again and wait to see if the new temperature is better. It may also happen that you turn the thermostat up too high and it becomes too warm in your apartment. Then you go back to the thermostat and turn it down a bit this time. This process continues until you find the perfect temperature. So, what you're doing is to adjust the thermostat, feel or let's say measure the difference to your feel-good temperature, and adjust the thermostat into that direction. Essentially, neural networks are doing the same thing. Our thermostat in this case are the weights in our neural network, which we adjust little by little to approach the perfect result. Before we let our neural network learn, the weights are randomly initialized. They are assigned a random value. To simplify things, I have omitted the bias in this illustration. Let's assume that our illustrated perceptron with these weights comes to a result of 0.4. However, the correct result is 0.6. During learning, the weights are adjusted so that we come to a prediction of 0.5. Although the difference between our estimator and the actual value has become smaller, the model has not yet learned the true relationship between input and target value, and the weights need to be adjusted further. Only after a further adjustment of the weights, the model becomes able to predict the actual value. But how do we actually measure the error between the prediction and the true value? That's where the so-called cost or loss function comes into play. It measures the error between the prediction and the actual value. One common loss function is the mean squared error, or MSE for short. It calculates the average of the squared differences between the predictor and the target value. If we only had one measurement, calculating the average value would be pointless. Instead, the error calculation is described as x0 times w0 plus x1 times w1, which is, in other words, our y-hat predictor, minus the actual measurement. Squaring the difference makes larger errors penalized more heavily than smaller ones. But when we have multiple measurements, we pass each measurement through the model with the same weights and then compute the mean squared error from all predictors. There are of course many other loss functions. Essentially, any function that can measure an error can serve as a loss function. Here are a few of the common loss functions categorized by regression and classification problems. Now we understand the theoretical setup of a neural network and we are aware of a variety of loss functions to measure the model's error. But how do we figure out how much each weight contributes to the error? That's where backpropagation comes in. This is an algorithm that feeds the error from the output of the neural network backwards through the hidden layers to the input layers. The mathematical part of this is probably one of the most difficult things in deep learning. During backpropagation, the gradients of the loss function are calculated in relation to the weights and biases of the network. These gradients are then used to update the weights and optimize the model by minimizing the error. Even though backpropagation is one of the core components of deep learning, we have decided not to delve into the mathematical details here. However, if you plan to work with more complex frameworks after this course, it is advisable to get a deeper understanding of backpropagation. For this course, just remember the following. After the forward pass, which is the process of passing our input data through the neural network, we calculate the loss based on the loss function. Remember that the loss is a measurement of the error between the predictor and the actual value. Once we have calculated the loss, we propagate the error backward through the model and compute the gradients of the weights and biases. With these gradients, we can determine how each weight should be adjusted. And that leads us to the last question of this lesson: how to update weights and biases based on the gradients. This is handled by an optimizer. There are many optimizers, but we will start by focusing on the gradient descent optimizer. Let's say we have only one input feature and thus only one weight in our neural network. And let's assume we had the time to test every possible weight to plot the resulting loss with the blue curve. After the random weight initialization, we are right here. Now, using backpropagation, the error has been propagated through our model and we obtain a gradient. To adjust the weight, we multiply the magnitude of the gradient by a small number called the learning rate and adjust the weight by this amount. This way we get a new weight and we pass our data through the model once again. We then get another gradient and adjust our weight according to the learning rate. We repeat this process until we reach the function's minimum. The learning rate is a so-called hyperparameter, which means it's something we, as users, need to define. Google provides a very good interactive tool to illustrate the effect of the learning rate onto the weight adjustment and thus on the learning progress. We are able to choose a custom learning rate and take manual optimization steps with each click on the step button. Thereby, the red dots represent the weights with the corresponding loss. With each click, a forward pass with the current weight is executed, followed by the calculation of the loss, the backpropagation, and the calculation of the new weight under the defined learning rate. This happens so fast that we just see the new red dot, representing the new loss and the new weight, which has been calculated. With a learning rate of 0.01, a lot of iterations are necessary, as the steps that are taken are very small. So let's increase the learning rate to 0.1. This way, it only takes a couple of iterations until we reach the optimum. Increasing the learning rate too much, for example to 1.0, we will overshoot the optimum each time and move further away from it. So selecting the suitable learning rate is crucial to train a model. Let's go back to our optimizers that handle each optimization step. The problem with gradient descent is that we need to pass all the data through our model before making a weight adjustment, and that takes a lot of time. To speed up model optimization, we can use stochastic gradient descent instead. In this approach, subsets of the training data are formed and the weights and biases are adjusted after each subset. Here's an example. We have 12 observations or 12 data points that we want to pass through our model. Before doing that, we divide our data into batches. We then pass the first batch through our model and adjust our weights right after this batch. Next, we feed the second batch into the model and adjust the weights again right after this batch, and so on with the final batch. With this method, we can adjust our model 3 times in one pass through all the observations, compared to just one adjustment with gradient descent. By the way, going through the whole dataset is called an epoch. These illustrations show the difference between gradient descent and stochastic gradient descent. In gradient descent, we look at all the data first to calculate a loss based on all errors. This gives the algorithm a very precise idea of which direction the weights need to be adjusted and gradually approaches an optimum. You can compare the gradient descent algorithm to a very cautious hiker walking down a mountain who first studies the map carefully, looks around to see which way leads to the valley, and then takes a step before checking again. On the other hand, stochastic gradient descent adjusts the weight several times per pass through the data. The loss is calculated only on a subset of the errors, which may not lead to the most accurate gradients. You can think of stochastic gradient descent as a somewhat tipsy hiker stumbling down the valley. He might walk a little detour sometimes, but because he moves quickly, he reaches the valley faster. To wrap up, let's review the key terms we need to remember for the rest of the course. First, epoch. Although I have mentioned epochs only once in this lesson, it's an important concept. An epoch is one cycle through the full training dataset. The batch is the subset of the training dataset and codes for the number of observations processed by the model before weights are adjusted. Hence, epochs and batches go hand in hand. We can have several batches per epoch. The loss function measures the difference between the predicted output and the real value. The learning rate is a crucial parameter that we have to set by ourselves. It's the proportion of the gradient used to calculate the weights adjustment. The optimizer is the method to adjust the model's parameters to minimize the loss function. One of its inputs is the learning rate itself. And finally, activation functions. These are the functions used to introduce nonlinearity to the model's architecture. For Python, there are many frameworks that make it easier to program and train a neural network. The major frameworks are PyTorch, TensorFlow, and Keras. PyTorch and TensorFlow are low-level libraries, meaning you have to handle much of the forward and backward pass yourself. PyTorch is developed by Meta AI and TensorFlow is developed by Google. While these frameworks offer a lot of flexibility, they can be quite complex for beginners in deep learning. So we will use Keras. Keras, although it's built upon TensorFlow and is now fully integrated into it, offers a more modular approach, making it easier to use. Here's a note. In this course, we'll focus solely on sequential models. These models have hidden layers that only pass their information to the subsequent layers. It's a sequential chain of input data, hidden layers, and output data. Such a sequential model is created in Keras with the expression tensorflow.keras.models.sequential. Initially, we'll work with simple artificial neural networks, or ANNs in short. These will mainly consist of what we call dense layers, which are essentially the same as the neural layers we've discussed so far.